When we look out into space, we think we're seeing the universe as it is: brilliant galaxies, glowing nebulae, exploding stars. But what if all of that is just the surface? What if the real universe, the one that governs structure, shapes galaxies, and commands the dance of gravity, is something we cannot see? This is not science fiction. It is scientific reality, because most of the universe is missing from view. Not missing in substance, but missing in light. Roughly 85% of the matter in the universe is dark, invisible, mysterious, and silent. It doesn't shine. It doesn't reflect. It does not interact with electromagnetic waves. It's there, but only through its gravity do we know it exists. This is dark matter, one of the greatest enigmas in all of science. For decades, we've struggled to learn what it is. We've built experiments, developed theories, and scanned the cosmos. And now, with the launch of the James Webb Space Telescope, we may be on the edge of a breakthrough, not by seeing dark matter directly, but by watching what it does. The unseen is finally casting visible shadows. The story of dark matter begins not with a discovery, but with a discrepancy. In the 1930s, astronomer Fritz Zwicky observed something strange in a distant galaxy cluster. The galaxies were moving too fast. Their speeds defied the pull of the visible mass. Something else, some extra source of gravity, had to be holding them together. He called it dunkle materie, dark matter. His idea was radical. It was largely ignored. It wasn't until the 1970s, when Vera Rubin began meticulously measuring the rotation curves of galaxies, that the mystery returned with force. Rubin found that stars far from the centers of galaxies were orbiting much faster than Newtonian physics allowed. The galaxies should have unraveled, flung their outer stars into deep space. But they didn't. They held together. The only explanation: these galaxies were embedded in vast halos of invisible matter. Rubin's work not only confirmed Zwicky's suspicions, it transformed the problem into a cosmic puzzle. Fast forward to today. We've built incredible telescopes. We've sent probes across the solar system. But nothing compares to the James Webb Space Telescope. This is not just an upgrade over Hubble. It is a fundamental shift in how we observe the cosmos. With a mirror over 6.5 meters wide and detectors chilled to near absolute zero, Webb sees the universe in the infrared spectrum, where heat, not light, reveals the most ancient and distant structures. Why is this important for dark matter? Because dark matter's influence is clearest in the early universe, in the way the first galaxies formed, the way light bends around massive clusters, and the way the cosmos organized itself over billions of years. James Webb can look back over 13 billion years, revealing galaxies at their infancy. And through their shapes, alignments, and motions, we can begin to understand how invisible matter molded them. Dark matter doesn't glow, but it sculpts. Webb sees the sculptures. How do you see something that doesn't emit light? You don't look for the thing itself. You look for what it moves. One of the most extraordinary methods for detecting dark matter is through gravitational lensing, the warping of light caused by gravity. Imagine a distant galaxy billions of light years away. Now place a massive object, like a galaxy cluster, between that galaxy and us. According to Einstein, the gravity of the cluster bends the light, magnifying and distorting it like a funhouse mirror in space. With Webb's precision, these distortions are clearer than ever before, and they don't match the visible mass. The light is bending too much. There's more gravity than there are stars, more pull than there is gas. That missing mass, that extra gravity, is dark matter. It doesn't shine, but it makes its presence known by how it bends the path of photons that pass nearby. James Webb is mapping these lensing events across cosmic time, turning the warped light of the early universe into a map of the unseen structure beneath it all. Across hundreds of millions of light years, galaxies are not randomly scattered. They are strung along vast filaments, woven into a pattern of threads and nodes, separated by immense voids. What formed this structure? Not light, not atoms, dark matter. It was the first to clump in the early universe. Long before stars ignited or galaxies swirled, dark matter began collapsing under its own gravity, pulling normal matter into its gravitational wells. James Webb is now looking into those deep recesses of time, watching as the earliest galaxies emerged. It sees baby galaxies, mere smudges of starlight, forming along the invisible highways laid down by dark matter. And by comparing these observations with simulations, we are beginning to confirm the models. Dark matter didn't just help form the universe, it architected it. In the grand sweep of the cosmos, it's easy to overlook the small things. But sometimes, the smallest galaxies, dwarf galaxies, give us the biggest clues. These faint, dim, often irregular systems are made up of very few stars, yet are held together with surprising strength. Why? Because they are dominated by dark matter. More than any other structures, dwarf galaxies are test cases, laboratories for studying how dark matter behaves on the smallest scales. And some of them don't behave as we expect. There are signs of dark matter being less cold than we assumed, or interacting with itself in ways our current models don't predict. With its exquisite sensitivity, James Webb can now detect these tiny galaxies across enormous distances and compare them across different epochs in cosmic history. The more we study them, the clearer it becomes. Dark matter may not be a single answer, but a whole family of mysteries. Dark matter remains one of the greatest frontiers in modern physics. We don't know what it is, but we know what it isn't. It's not made of atoms. It's not part of the periodic table. It doesn't respond to light, and it doesn't seem to fit within the standard model of particle physics, the framework that explains all known subatomic particles. So what is it? It could be a new particle, a WIMP, or weakly interacting massive particle. It could be something even more exotic, axions or dark photons, or perhaps evidence of a hidden sector of physics. James Webb won't detect those particles directly, but by revealing how the invisible shapes the visible, by showing us where galaxies form, how they cluster, how light is bent, it is giving physicists the context they need. A roadmap, a reality check, a universe that behaves according to rules we're only beginning to understand. We once believed the universe was defined by what we could see, but today, we know that the real architecture of reality is hidden from view. Dark matter is not a shadow cast by light. It is the framework into which light has fallen. And now, with the James Webb Space Telescope, we are finally seeing how that framework came to be. It's not a direct image of the invisible, but it's something just as powerful, the shape of what cannot be seen, traced in the motion of galaxies, in the bending of starlight, and in the silent pull of gravity. In every lensing arc, in every ancient galaxy, in every unexpected pattern, James Webb is telling us a story of a universe built on the unseen, a universe more mysterious, more elegant, and more astonishing than we ever imagined. We are not just discovering new objects. We are uncovering a deeper reality, one woven in darkness, but revealed by light.